Now we will talk about a particle moving on a circular path. If you remember, if we don't have uniform circular motion, the particle is moving on a circular path like this, we must have a tangential acceleration, tangential component of acceleration. So in our treatment of this problem in kinematics, we have found that this tangential acceleration was the rate of change of the speed of the particle. So we have the position of the particle given in terms of the radial unit vector r hat, r hat. The velocity is the derivative of the position vector with respect to time. So that's r dot r hat plus r hat dot. But r dot is dr dt. If this is a circular path like this, the radius is constant, so that is 0. So that gives us r hat dot, which is r theta dot theta hat, which is, because theta dot is the angular speed omega, omega r theta hat. And acceleration is omega dot r theta hat plus omega r dot theta hat plus omega r theta hat dot. Now omega dot r would be the rate of change of the speed, because the speed is omega r and r is a constant, so omega dot r is the rate of change of the speed in theta hat direction. Omega r dot is 0 because r dot was 0, the radius is a constant, and omega r theta hat dot gives us minus omega square r hat, or our usual centripetal acceleration minus v square over r hat. So we have this tangential acceleration, which is dv dt in this problem, and according to Newton's second law, the total force must have a radial component and a tangential component, where the tangential force would be m dv dt, and the radial force would be mv square over r in minus r hat direction. Okay, let's look at a few examples. A small sphere of mass m is attached to the end of a cord of length capital R and set into motion in a vertical circle about a fixed point O as illustrated in figure. So we have this small sphere that is moving on this vertical circle under the influence of gravitational acceleration. Determine the tangential acceleration of the sphere, tension in the cord at any instant when the speed of the sphere is v and cord makes an angle theta with the vertical. So as usual, we start with the free body diagram of the sphere. We have to identify the forces acting on it. Now on the sphere we have the weight mg, and then we have, as you can see here, the tension T. Let's say that it's making an angle theta with the vertical, so this is going to be making an angle theta with the vertical. So if this is our center, O, r hat would be pointing this way and theta hat would be pointing perpendicular to it in the tangential direction. Now we can start writing the forces acting on this. The net force in the radial direction would be equal to, because this is our radial direction, I have to take the component of mg on this axis, that is mg cosine theta. And as you can see, this is in plus r hat direction. And on top of this, we have the tension in the cord that is pointing towards the center. So this would be in minus r hat direction, so minus t. And the centripetal acceleration is in minus r hat direction, so it's minus v squared divided by capital R. Okay, so just to remind you, using the r hat and theta hat vectors here, because we have minus t in r hat direction plus mg cosine theta in r hat direction, that is equal to minus mv squared over r in r hat direction. So this is actually a vector equation. So I'm considering these the signs of the vectors according to the unit vectors. Now the tension is therefore mg cosine theta plus mv squared divided by r. So this was one of the questions. What is the tension when the speed is v, the angle is theta? This is the tension when the speed is v and angle is theta. Now I can write the tangential force the tangential force comes from not tension but the component of mg on theta hat, which is mg sine theta, and you can see it's in theta hat direction, so this is mg sine theta in plus theta hat direction, which is mass times the tangential acceleration. The mass cancels and we're left with a tangential acceleration which is equal to g sine theta. So it's plus g sine theta, theta hat. So here we have chosen theta hat in positive in counterclockwise direction. Okay, so we can move on to another example. Example 2. A roller coaster car has a mass of 500 kilograms when fully loaded with passengers. The path of the coaster from its initial position shown in figure to point B involves only up and down motion. So you can see it's moving on the circular path with up and down motion as seen by the riders, with no motion to the left or right. If the vehicle has a speed of 20 meters per second at point A, what is the force exerted by the track on the car at this point? What is the maximum speed of the vehicle can have at point B and still remain on the track? So on the verge of losing contact with the track. Assume the roller coaster tracks at points A and B are parts of the vertical circles of radius 10 meters and 15 meters respectively. So I start with free body diagram at point A, where I have the weight mg pointing down. So you would have this weight pointing down, and then you would have the normal force pointing up. So this would be mg. This is our normal force. So you can see because this is part of a circle and the center is up above, we have the r hat vector pointing down. So r hat vector is pointing down, the normal vector is n, and mg is pointing down. So if I look at the net radial force, Fr, this would be mg in r hat direction minus n r hat direction, gives us minus mv square over the radius of that circle, r1. So I see that the normal force must be equal to mg plus mv square divided by r1. So this is the force exerted by the track on the car, which has a mass of 500 kilograms. So 500 kilograms times 9.8 meters per second square plus 500 times 20 meters per second square divided by r1, which is 10 meters. So we find the force exerted by the track on the car to be 24.9 kilonewtons. So let me double check. The radius r1 was 10 meters, the mass is 500 kilograms, and we have a speed of 20 meters per second at point A, and that's the force exerted by the track on the car at this point. That's the normal force. Now in part B, we are at point B. Now at point B, we have the mg pointing down, the normal force pointing up like this again, and that would correspond to this free body diagram. Because the center of this circle is down here, r hat is pointing up like this. So if I write the net radial force, this would be n pointing up in r hat direction, mg pointing in minus r hat direction, minus mv square over r2, the radius of this circle. And what I want to do is to be on the verge of losing contact. So on the verge of losing contact, what would happen is the normal force, the contact force, would become 0. So this would mean that mg would be equal to m v max square divided by r2. The mass will cancel. So with this maximum speed of square root gr2, I would have loss of contact, so this would be 15 meters times 9.8 meters per second square. So I find that the maximum speed the car can have is 12.1 meters per second, and if the speed exceeds this value, so what would happen for v greater than v max? It will escape the track, lose contact with the track, and run away. Okay, so by analyzing the free body diagram at point A and point B, we were able to determine the force exerted by the track at point A and the maximum speed we can have, so that we won't fly away like this. Instead, we're going to stay on the track, and that maximum speed corresponds to the point at which the normal force exerted by the track would be 0. Okay. Now let's move on to another example. A single bead can slide with negligible friction on a stiff wire that has been bent into a circular loop of radius 15 centimeters as shown in figure. So this is basically the bead has the wire going through it, and this wire has a circular loop of radius 15 centimeters. It's in a vertical plane, so we have gravitational acceleration pointing in this direction, and it rotates steadily about its vertical diameter with a period of 0.450 seconds. So it's rotating like this. The position of the bead is described by the angle theta that the radial line from the center of the loop to the bead makes with the vertical. So this angle is theta. At what angle up from the bottom of the circle can the bead stay motionless relative to the turning circle? So as this rotates, the bead will stay motionless with respect to the circular wire at a certain angular position. So we want to know what is that angular position. If the period of revolution is 0.45 seconds and 0.85 seconds in part B, describe how the solution to part B is different from A. For any period or loop size, is there always an angle at which the bead can stand still relative to the loop? Are there ever more than two angles? Okay, the first thing I want you to notice here is that the radius of this circle, the circular motion the bead will perform when it's kept still with respect to the circular wire, is different from the radius of the circular loop. So that radius, capital R, which I'm going to call capital R here, you can see, that would be R times sine theta. Okay, so my first observation is that capital R is equal to R sine theta. The bead performs basically a uniform circular motion with a radius capital R equals R sine theta. Now, when I look at the free body diagram for the bead, I see that because there's a gravitational acceleration pointing down, this has its weight, and then because it's in contact, physical contact with the circular wire, there will be a normal force acting on it, which makes an angle theta with the vertical. So this is my y-axis, this is my radial axis. The net force on the y-axis will be 0. So that means n cosine theta minus mg will be 0. Therefore, I find that the normal force exerted by the wire should be mg divided by cosine theta. There is no motion on the y-axis. The radial component of the force, Fr, would be equal to n sine theta, but because the center is here, r hat would be pointing in this direction, so it is minus n sine theta r hat, which is minus mv square over r hat. So this would be the radial force. So that would give us, by substituting n equals mg over cosine theta, mg over cosine theta sine theta is equal to mv square over capital R. So m divided by r sine theta, which is capital R, multiplied by v square, where v square is 2 pi r sine theta, which is the circumference of the circle divided by circular path divided by the period t squared. So m's will cancel here. M's will cancel. So we will have g times sine theta divided by cosine theta is equal to 4 pi square r, because one of the r's will cancel, 4 pi square r sine square theta divided by t square sine theta. Now, because sine theta can be 0, it's better not to cancel these angles and keep it as it is. So this equation can be written as, in sine square theta parentheses, g over cosine theta sine square theta g over cosine theta minus 4 pi square r divided by t square. So this is equal to 0, so that the bead will stay motionless relative to the circular wire. So we're going to solve for the angle theta here. So you can see that this equation will have two solutions. For sine square theta equals 0. So this has two solutions for sine theta equals to 0. That would give us theta is equal to 0 or 180 degrees. So that means the bead can stay at the bottom of this loop right here, or it can stay at the top. Now, on the other hand, this equation has another solution, so that sine square theta equals 0, or this parenthesis is equal to 0. So that would give us g over cosine theta must be equal to 4 pi square r divided by t square. So for that solution, we would have theta is equal to cosine inverse t square g divided by 4 pi square r. So if we substitute the numbers here, cosine inverse, 0.45 seconds was the period square, 9.8 meters per second square. Gravitational acceleration divided by 4 pi square times the radius of the circle was 15 centimeters, 0.15 meters in SI units. So this gives us 0.335, or the angle is 70.4 degrees. So this was our answer to part A of the problem. Now in part B, we're going to change the period to 0.850 seconds. So if we do that, then the solution theta equals 0 and 180 degrees, those would be possible. Again, theta equals 0 or 180 degrees, possible two solutions. And then the one in parentheses would give us theta is equal to cosine inverse of t squared g divided by 4 pi square r. And now we have the period different, 0.85 square times 9.8 meters per second square divided by 4 pi square 0.15 meters. That gives us cosine inverse of 1.2. So we know that this is not possible. Cosine is a function that oscillates between plus or minus 1, so that doesn't give any solution. So these are the only two solutions we can have in part B. Now part C asks me how these two solutions are different. Now in part B I have for t is equal to 0.850 seconds, we have only two solutions. Theta equals 0 or 180 degrees instead of three possible solutions. Part D asks for any period or loop size, is there always an angle at which the beat can stand still relative to the loop? Now you can see that sine squared theta equals 0 is independent of the radius of the loop and the period that we use, so that would always be a solution regardless of the size of the loop or the period. So theta equals 0 degrees or 180 degrees solutions are always valid because the condition sine squared theta equals 0 is independent of loop size or the period of revolution of the circular loop. In part E, are there ever more than two angles for this? Well, there are two angles, theta equals 0 and 180 degrees, always possible. And as shown in part A, we can have more than two solutions. We have at most three, or let's say we can have more than two solutions. We have at least two solutions for all cases, so as we have discussed in part D. Okay, so in this problem we had this bead that is connected to this circular wire, and as the wire rotates around its vertical axis, the bead stays motionless with respect to the wire, performing uniform circular motion. For a given period of 0.45 seconds and 0.85 seconds, we were asked to find the equilibrium angles for which this bead would stay motionless relative to the wire. So what we have done was draw a free body diagram for the bead, where we identified the normal force, the contact force between the wire and the bead, and mg the weight, and this gave us from the condition that there's no motion on the y-axis, normal force equals to mg over cosine theta, and we have to find the radial force minus n sine theta equals minus mv square over r, and we were careful about the radius of this circle being different from the radius of the circular wire. It is basically r sine theta equals capital R. And substituting for the normal force mg over cosine theta, we have obtained an equation for the angle theta, which says sine squared theta equals 0, and then this expression in the parentheses must be equal to 0. So this quantity in the parentheses equals to 0 gives us cosine inverse of t squared g over 4 pi square r, and I was careful about converting centimeters to meters here as well. So this gave us 70.4 degrees as one solution. There were two other solutions, 0 degrees or 180 degrees from sine squared theta equals 0. And these two solutions are always possible because they're independent of this parentheses, the quantity in the parentheses, and we find that actually for a certain period those are the only possible two solutions, because we can see that the quantity in the parentheses is greater than 1, cosine inverse of 1 doesn't exist, so that's not a possible solution. So we see that we have at least two solutions, and we can have more than two solutions depending on the period and the size of the loop.